Welcome back, everyone, to the deep dive. Really excited about today's topic. We're diving into something maybe a bit technical, but super important, making data transfers better, specifically within those complex ORM systems, extract, transform, load ETL. Getting that right is key. But the tricky part, it's always those complex relationships between data entities in ORM. It's like a tangled web. Get it wrong, and bam, slow performance, maybe even data integrity headaches.
That's spot on. And, the traditional ways like topological sorting, they're good for order, making sure parents load before children, that kind of thing, referential integrity. But they don't really tell you the weight or the burden of moving a specific piece of data.
Right, just the sequence, not the impact.
Exactly.
So that's what we're digging into, this new idea called movement weight. The goal here is to turn those messy dependencies into, well, useful insights for actually optimizing things, moving beyond just A, then B. Okay, so let's get into it. What is movement weight, really? How's it calculated?
Right. So think of movement weight as a score, basically. It quantifies the total impact, structural dependence and impact of any given entity in your ORM model. Higher weight means more baggage, more burden during transfer.
More baggage, I like that.
Yeah.
So how do you figure out that score?
Well, it starts simple enough. You look at the entity's own vertex weight, which is basically just, the approximate size of its row in the database. Bytes.
Okay, its own size.
Yeah. But then, and this is the clever bit, it uses a recursive formula. It works backwards through the dependency order, reverse topological sort, and it adds up its own weight plus the vertex weights and the movement weights of everything that directly depends on it.
Ah, so it's not just its own size, but the size of everything downstream that relies on it.
Exactly. It captures that whole ripple effect, the cumulative load.
Okay, that sounds powerful.
Huh.
But I imagine getting an algorithm like this working perfectly, especially with real-world, messy ORM data, wasn't exactly straightforward.
Oh, definitely not. The journey to get this stable actually taught us a lot.
Like what kind of gremlins showed up?
Well, first off, we hit this bizarre thing we called the false cyclic dependency anomaly. The algorithm kept thinking there were loops in the data graph where, well, there weren't any. It was getting stuck.
Loops? How?
It turned out the counter we used, the indegrees counter, which tracks incoming connections, was a bit too enthusiastic. Say you had an artist entity pointing to an area entity through 3 different fields, like at many-tune relationships.
Right.
The counter was incrementing 3 times for area, making it look like artist depended on area 3 separate times, which confused the sorting logic into thinking there was a cycle.
Ah, so it was counting fields, not unique class connections.
Yeah.
That is subtle.
It really is, and it highlighted just how meticulous you have to be when you build that graph representation.
So what was the fix?
Pretty elegant, actually. We switched to using a hash set. That data structure only allows unique entries, so it automatically ensured we only counted the dependency between artist and area once, regardless of how many fields linked them.
Okay, smart. That cleared up the phantom cycles.
Instantly. Stabilized the whole sorting process. But then another issue popped up.
Of course. What was next?
We called it the stagnant movement weight anomaly. Even with the sorting fixed, some entities, like artist, had these suspiciously low movement weights that just wouldn't change much. But things that depended on artist, like artist credit, had much higher weights, and they fluctuated. It didn't add up.
So the dependence weights weren't rolling up correctly to the parent.
Precisely. The contributions weren't summing properly. We realized our initial graph building focused heavily on at many-tune and at one-tune links, looking from the child up to the parent. We weren't fully utilizing the inverse relationships, like at one-tomity defined on the parent side, to make sure we registered all the direct dependents for the summation.
Another case of needing the complete picture of the relationship.
Exactly. Got to capture it from both directions to be thorough.
Okay, 2 hurdles down. You mentioned a third. The mutating priority anomaly. That sounds kind of ominous.
Yeah, that one was a bit of a facepalm moment, honestly. We found a completely separate method in a different class even that was messing with our carefully calculated movement weights.
How?
This other method, process graph by breadth first, I think it was meant to track how often nodes were visited for a totally different purpose. But somewhere in its logic, it was accidentally recalculating and overwriting the movement weight values we'd already stored.
Oh, wow. So completely unrelated code was just silently corrupting the data.
Yep. It was a stark reminder of how interconnected things can be and how side effects can bite you if you're not careful.
So the fix was, don't tell me it was complicated.
Thankfully, no. The fix was just commenting out that specific line of code that did the overwriting. Simple, but absolutely critical.
Phew. Okay, so after navigating all those anomalies, where did that leave movement weight? Does it work reliably now?
Yes, absolutely. With those issues resolved, the algorithm consistently produces stable logical weights. And we see patterns that make sense, like type entities, think area type or artist type, they often end up with higher movement weights.
Higher than the actual entities they describe, like area or artist. Why is that?
Because those type entities often act as parents or dependencies for many other entities. So area type might have a weight like 22,000, while area itself is maybe 14,000. Artist type around 17,800, artist way down at 2,700. It reflects that they aggregate the impact of all the things that depend on them, which is exactly what the metric is supposed to do. It validates the approach.
That makes sense. It really shows how this kind of metric moves beyond just ordering things. It gives you a real sense of the cost or load involved, helping you pinpoint potential bottlenecks, right, for smarter ETL.
Precisely. Intelligent resource allocation, better bottleneck identification. That's the promise.
So looking ahead, where could this go? What's the bigger picture?
Well, imagine automating the discovery of these entities across your whole system, your class path. Or even better, building visualization tools. Imagine actually seeing the graph with nodes sized by their movement weight. You could instantly spot the heavy hitters.
That would be powerful.
Yeah.
Seeing the hidden burdens.
Yeah, making the invisible visible.
It really makes you think, doesn't it? How understanding the weight of information, not just its sequence, could change how we tackle complex systems. Maybe even how we filter all the information coming at us every day. What carries the most downstream impact? Something to consider.